WIMPs, weakly interacting massive particles. For 30 years, they were the favorite. Here's the pitch: a particle about as heavy as 100 protons, born in the first fractions of a second after the Big Bang, feeling gravity like everything else, but almost nothing else. No light, no charge, no handshake with ordinary matter except the faintest possible nudge. The math behind them is suspiciously beautiful. Physicists call it the WIMP miracle. Take a particle with roughly the mass and interaction strength predicted by supersymmetry, a totally separate theory built to fix problems in the standard model, and run the numbers on how much of it would survive from the early universe. The answer lands almost exactly on the amount of dark matter we actually observe. Not close. Almost exact. That kind of coincidence doesn't happen by accident. Or so the thinking went. So the hunt began. Detectors buried a mile underground, in old mines in South Dakota and Italy, wrapped in lead and ancient water to block out every cosmic ray, every stray particle that isn't the one they want. Tanks of liquid xenon, cooled and purified beyond anything found in nature, sitting in the dark for years, waiting for a single WIMP to bump into a single xenon nucleus and produce one faint flash of light. Here's the twist. After 3 decades and billions of dollars, nothing. Not one confirmed WIMP. Each new detector generation rules out a wider slice of the parameter space where WIMPs were supposed to hide. The favorite candidate has been slowly cornered into smaller and smaller rooms. That doesn't mean WIMPs are dead. It means the easy version is dead. Let that sink in. The most elegant answer in modern physics might simply be wrong, and nobody ruled it out with a bang. They ruled it out one empty detector year at a time. Consider the scale of the effort. The Lux Zeppelin experiment, buried a mile down in a former gold mine in South Dakota, uses 10 tons of liquid xenon, cooled to almost the density of solid rock, sitting inside tanks of ultra pure water inside a cavern blasted from ancient stone. The entire structure exists to filter out everything except one theoretical particle. Cosmic rays get stopped by a kilometer of granite overhead. Radioactive contamination gets scrubbed down to levels measured in parts per trillion. And still, after all of that engineering, after all of that patience, silence. Some physicists now quietly admit the WIMP miracle might have been a mirage, a coincidence of the math, not a signpost pointing to reality. Others argue the particle is simply lighter or heavier or sheer than first assumed, and the next generation of detectors will finally catch it. Either way, 3 decades of the field's best minds and biggest budgets have bought us an extraordinarily precise map of where WIMPs are not. But if the elegant particle isn't showing up, maybe the universe hid dark matter somewhere stranger, somewhere almost too small to imagine. Axions. If WIMPs are missing because they're too rare, axions are hiding because they're too light. Picture a particle with a mass maybe a trillion times smaller than an electron. So light, it barely counts as a particle at all, more like a wave rippling through space, a field that fills every cubic centimeter of the cosmos at once. Here's where it gets strange. Physicists didn't invent axions to explain dark matter. They invented axions to fix an unrelated problem: why the strong nuclear force, the one binding atomic nuclei together, doesn't violate a basic symmetry of physics called charge parity symmetry, when in principle it easily could. The axion was a patch, a mathematical fix proposed in 1977 for a completely different puzzle. And then someone noticed, if axions exist, the early universe would have produced huge numbers of them, and they would behave exactly like cold, invisible, gravity only dark matter. A patch for one problem might quietly be solving another. The search for axions doesn't look like the search for WIMPs. No underground tanks. Instead, powerful magnets and ultra-sensitive microwave cavities, tuned like radios scanning for one specific frequency, hunting for the whisper-thin signal of an axon converting into a photon inside a magnetic field. It's slow. It's been running for decades. And the sensitivity keeps climbing. Here's the fact that changes everything about how we think of these particles. Trillions of axions could be passing through your body right now, through this room, through the entire Earth, leaving no trace, feeling no resistance, and we would never know. An invisible tide permanently rising and falling around every atom you're made of. Nobody has caught one yet. But unlike WIMPs, the Axion hunt is still in its early chapters. Most of its possible mass range hasn't even been searched. If dark matter turns out to be a field instead of a particle, everything about how we picture stuff quietly breaks. The instruments hunting axions look almost quaint next to the underground xenon tanks, copper cavities the size of a coffee can, chilled near absolute zero, sitting inside superconducting magnets far stronger than anything in a hospital MRI machine. Experiments like ADMX at the University of Washington have been scanning frequency by frequency year after year, the way an old radio operator might scan a dial searching for one faint station in an ocean of static. Each scan covers a sliver of possible axion mass. There are decades of sliver left to check. What makes axions genuinely different from WIMPs isn't just the size, it's the texture. A WIMP would arrive as a particle, a single hit in a detector, discrete and countable. An axion field would be smoother, a wave washing continuously through everything, oscillating at a frequency tied directly to its mass. Detecting one wouldn't mean catching a bullet. It would mean picking out one exact, impossibly quiet note in an otherwise silent universe. Light and elusive on one end. But what if dark matter isn't exotic at all? What if it's just a familiar particle that's been hiding in plain sight? Sterile neutrinos. We already know regular neutrinos exist. Trillions pass through you every second, produced by the sun, by nuclear reactions, by the Big Bang itself. Nearly massless, nearly undetectable, but real, measured, confirmed. Here's the reframe. What if there's a fourth kind? 3 known neutrino flavors interact weakly, but they interact through the weak nuclear force. A sterile neutrino wouldn't. It would only feel gravity. The name says it all. Sterile, because it refuses to participate in anything except pulling on the universe with mass. The appeal is that sterile neutrinos aren't a totally new invention bolted onto physics from nowhere. They're a natural extension of a particle we've already confirmed exists. Add one more entry to a family we already know is real, give it the right mass, somewhere in the kilo electron volt range, thousands of times lighter than a proton, and it can behave as dark matter. There was even a moment of excitement. In 2014, astronomers spotted an unexplained X-ray signal at 3.5 kilo electron volts coming from galaxy clusters and the Andromeda galaxy, exactly the kind of faint signature a decaying sterile neutrino might produce. Papers were written, conferences buzzed. Here's the fact that changes everything. Follow-up observations with sharper instruments couldn't confirm it. The signal, if it was ever really there, refused to reappear cleanly. Sterile neutrinos went from maybe we just found it back to still theoretical within a few years, a reminder of how fast the ground can shift in this hunt. They're not ruled out. They're just waiting the same way they've been waiting since the idea was first proposed in the 1990s. A familiar face in an unfamiliar disguise, still uncaught. There's a reason physicists keep circling back to this candidate despite the false alarm. Sterile neutrinos would solve more than one problem at once. They could help explain why regular neutrinos have such a tiny but non-zero mass, a puzzle in its own right. Some versions could even help explain the matter-antimatter imbalance that let any of us exist at all. A single new particle quietly patching 3 separate cracks in the standard model, that's the kind of efficiency that keeps an idea alive even after its best piece of evidence falls apart. So far, every candidate has been a new kind of particle. But what if dark matter isn't a particle you've never heard of? What if it's something you already understand, just impossibly compressed? Primordial black holes. Not the black holes formed when massive stars collapse. These would be older than the first star by billions of years. Here's the reframe. These black holes wouldn't come from a dying star at all. They'd come from the raw density chaos of the Big Bang itself, in the first fraction of a second, when random regions of space were compressed so violently that gravity won instantly, no stellar life cycle required, no fuel to burn first. Pockets of the infant universe simply collapsing directly into black holes. The range of possible sizes is staggering. Some models predict primordial black holes as light as an asteroid, others as heavy as 1,000 suns, all formed in that same first instant, all invisible, all potentially still out there in numbers vast enough to account for a meaningful slice of the universe's dark matter. Here's what makes them different from every other candidate on this list. Primordial black holes aren't new physics. They don't require an undiscovered particle, an undiscovered force, or an undiscovered field. General relativity, the theory Einstein wrote down over a century ago, already permits them. That's either the most economical solution here or a sign of how desperate the hunt has become, depending on who you ask. The one fact that changes everything. Astronomers have actually gone looking, and the search rules things out fast. Gravitational microlensing surveys, watching for a black hole's gravity to briefly brighten a background star as it drifts past, have already excluded primordial black holes as the dominant form of dark matter across a huge range of masses. Not gone. Just squeezed into narrower and narrower gaps, the same way WIMPs were. Let that sink in. Somewhere out there, drifting silently through the galaxy, there might be black holes older than every star in the sky, born before matter had even finished forming, and we'd only ever see one by the flicker it leaves behind when it eclipses something bigger than itself. There's an added wrinkle that makes this candidate hard to dismiss entirely. In 2015, the LIGO Observatory detected gravitational waves from two black holes merging, each roughly 30 times the mass of the Sun, heavier than most astronomers expected from ordinary stellar collapse. It reignited the primordial black hole idea overnight. Maybe some of the black hole mergers LIGO keeps finding aren't dead stars at all. Maybe a fraction of them are relics from the Big Bang itself, finally colliding after roaming the universe for 13 billion years. If ancient compressed points of gravity are one option, there's a simpler, almost boring cousin waiting in the wings, ordinary objects, just too dim to see. MACHOs, massive compact halo objects. This is the twist item, the candidate that looked like the obvious answer and then quietly wasn't. Here's the pitch, and it's the simplest one on this list. What if dark matter isn't exotic at all? What if it's just normal matter that's too faint to spot? Brown dwarfs that never ignited into stars, rogue planets flung out of their systems, dead white dwarfs, ancient black holes formed the ordinary way, all drifting through galactic halos, all made of completely ordinary atoms, just dark because they don't shine. It's an elegant idea because it requires zero new physics, no new particles, no new forces. Just more of the same stuff we already know, hiding in the dark corners of every galaxy. Here's the fact that changes everything, and it's the reason MACHOs are the twist in this story. Astronomers tested it directly. Using the same gravitational microlensing technique used to hunt primordial black holes, teams like the MACHO Project and EROS spent years watching millions of stars in the Large Magellanic Cloud, waiting for the telltale brightening caused by a compact object drifting in front of them. They found some, just not nearly enough. The lensing events observed account for only a small fraction of the dark matter needed to explain galactic rotation curves. MACHOs, as a full explanation, are mostly ruled out. Let that sink in. The most intuitive, least exotic answer to one of physics' biggest mysteries turned out to be almost entirely wrong. Ordinary matter, however dim, however dead, simply isn't out there in the quantities required. Whatever dark matter is, the evidence increasingly says it has to be something genuinely new. There's a second independent nail in this coffin, and it doesn't come from lensing at all. It comes from the Big Bang itself. The relative abundance of hydrogen, helium, and lithium formed in the first few minutes of the universe depends sensitively on exactly how much ordinary matter existed back then, a process called Big Bang nucleosynthesis. Run the numbers, and the amount of ordinary matter implied is far too small to account for all the dark matter observed today. Even if every brown dwarf, every rogue planet, every dead star in every galaxy were somehow dark matter, there simply isn't enough ordinary matter in the universe's own recipe to add up. MACHOs weren't just outnumbered by the lensing surveys. They were outnumbered by the arithmetic of creation itself. So if it's not hidden stars and dead planets, and if it's not fully confirmed as any single new particle either, What if we've been asking the wrong question about how dark matter behaves at all? Self-interacting dark matter. Every candidate so far assumes dark matter particles ignore each other completely, gravity only, no collisions, ghosts passing through ghosts. This one breaks that assumption. Here's the reframe. What if dark matter particles do bump into each other, just never into us? A private physics, a hidden sector with its own forces, invisible to every detector built for ordinary matter, but very real to itself. The motivation isn't guesswork, it comes from a mismatch. Standard cold dark matter simulations predict galaxy cores should be dense and sharply peaked, like a spike. Real galaxies, especially small dwarf galaxies, tend to have flatter, more spread out cores. Standard simulations also predict way more small satellite galaxies around big ones like the Milky Way than we actually observe. Give dark matter particles even a small ability to interact with each other, and both problems start to ease. Collisions gently redistribute the density, smoothing out the spike, thinning the swarm of satellites. Here's the fact that changes everything. This idea doesn't replace WIMPs, Axions, or sterile neutrinos, it modifies them. Self-interacting dark matter isn't a rival particle so much as a rival personality trait, that could belong to almost any of the other candidates, if the underlying physics allows for a hidden force between them. It's a strange kind of answer, not what dark matter is made of, but how it behaves once it exists. And it means the smallest, quietest galaxies in the universe, the dim dwarf galaxies most people never think about, might be the best laboratories we have for testing what dark matter does when nobody's watching. The clearest testing ground might be colliding galaxy clusters, the same events used to confirm dark matter exists in the first place. If dark matter particles bump into each other even occasionally, a collision between two galaxy clusters should slow the dark matter down slightly, dragging it behind the stars the way friction drags gas. Standard cold dark matter predicts almost zero drag. Self-interacting models predict a small, measurable offset. Astronomers are now combing through cluster collisions across the sky, hunting for exactly that signature, a few thousand light years of lag that could tell us whether dark matter is a crowd of silent strangers or a crowd that occasionally shoves. Every candidate up to now assumes dark matter is a substance, a particle, a swarm, a hidden population of compact objects. But what if that entire premise is wrong? MOND, modified Newtonian dynamics, the alternative framework, and it isn't a particle at all. Here's the reframe, and it's the biggest one on this list. What if there's no missing matter? What if the missing mass problem doesn't need mass because our law of gravity is simply wrong at extremely, extremely low accelerations, the kind found at the edges of galaxies, far weaker than anything we can test in a lab or the solar system? MOND proposes a modification to Newton's second law itself, tweaking how gravity behaves below a specific acceleration threshold. Do that, and remarkably, a single simple formula predicts galaxy rotation curves with startling accuracy, often better than dark matter particle models fit to the same galaxies, without needing to invoke a single invisible particle. That's the appeal. That's also the problem. Here's the fact that changes everything. MOND explains individual galaxy rotation beautifully, but it struggles badly at larger scales. It has real trouble accounting for the gravitational lensing seen around colliding galaxy clusters, most famously the bullet cluster, where the mass inferred from lensing is visibly spatially separated from the visible hot gas, a separation that's almost impossible to explain without some invisible substance actually being there, pulled apart from ordinary matter by a collision. MOND also struggles to match the fine structure seen in the cosmic microwave background without extra add-ons that start to look suspiciously like dark matter again, just wearing a different name. So MOND isn't dead, and it isn't crowned either. It's a genuine alternative framework, taken seriously by working physicists, that succeeds exactly where the particle models struggle most, small galaxies, and struggles exactly where the particle models succeed most, colliding clusters and the infinite universe. Two frameworks, each strong where the other is weak. Let that sink in. Some researchers have tried to build a bridge between the two ideas entirely. Theories where a modified force and a light exotic particle work together, each covering the other's blind spot. It's a sign of how unresolved this question still is. Nearly a century after the first hints of missing mass, the two leading philosophies for explaining it, add invisible stuff or rewrite the law of gravity itself, still haven't been reconciled into one clean answer, and both camps can point to real, hard-won observational victories. So after 7 candidates, heavy particles, feather light fields, disguised neutrinos, ancient black holes, dead stars, hidden forces, and modified gravity itself, where does that leave us? Here's the part that should genuinely bother you. We have never directly detected dark matter. Not once. Not a single confirmed particle in a single detector anywhere ever. Every candidate on this list remains technically unconfirmed, and yet almost nobody working in the field seriously doubts dark matter exists. Here's why. Galaxy rotation curves were the first clue back in the 1970s when Vera Rubin measured how fast stars orbit at the edges of spiral galaxies. Newtonian gravity, using only the visible matter, predicted those outer stars should orbit slowly, the way outer planets orbit the sun slower than inner ones. They didn't. They moved just as fast as stars near the center, as if something invisible, far more massive than the visible galaxy, was gripping the whole structure together. Gravitational lensing sealed it further. Massive objects bend light, predicted by Einstein and confirmed ever since. Measure how much a galaxy cluster bends the light of objects behind it, and you can weigh the cluster directly, independent of how much light it actually gives off. Again and again, the measured mass vastly exceeds the visible mass. The bullet cluster is the cleanest example. Two clusters collided, the visible gas slowed and piled up in the middle from friction, but the lensing mass, the actual gravitational weight, sailed straight through, separated from the gas entirely. Whatever's doing the pulling isn't the gas. It isn't the stars. It's something else, moving right through the collision untouched. And then the cosmic microwave background, the oldest light in the universe, a snapshot of the cosmos just 380,000 years after the Big Bang, carries tiny temperature fluctuations that encode, with extraordinary precision, exactly how much ordinary matter and how much extra invisible gravitational mass existed at that moment. The number that best fits the data, roughly 5 times more dark matter than ordinary matter, filling the universe since almost the very beginning. 3 independent lines of evidence. Different eras, different physics, different instruments, all pointing at the same invisible mass. That's not a coincidence you can wave away. So here is where the science actually stands, honestly. We know something is out there, gripping galaxies, bending light, shaping the structure of the entire cosmos at roughly 5 times the mass of everything we can see. We just don't know what it's made of. WIMPs are cornered but not dead. Axions are barely explored. Sterile neutrinos are unconfirmed but not gone. Primordial black holes are squeezed into narrow gaps. MACHOs are mostly ruled out. Self-interacting dark matter is a modifier waiting on a particle. MOND explains galaxies but fails clusters. Every galaxy you've ever seen a picture of is being held together by something no human being has ever touched, measured directly, or named with certainty. Let that sink in. Somewhere in this list is probably the answer. Or the answer is something on this list that nobody has proposed yet. Either way, 80% of the universe's gravity is currently unaccounted for, and the universe does not care that this bothers us. Not bad for stick figures on a rock.